The next part of our putting it together concept says, what is the minimum amount of carbon required to achieve equilibrium under these conditions? Knowing that the carbon did not play a role when we did our equilibrium expression, it is still part of the overall chemical equation, and there is a certain minimum amount of grams needed to start this reaction. It is not part of Kp expression, but it is indeed part of the chemistry. Here's what we know so far from the last problem, that at equilibrium we had a partial pressure of water as 2.672 atmospheres. Using this information and the stoichiometry, we can figure out the number of moles of water at the equilibrium. If PV equals nRT, let's pull out N, the number of moles of water at the equilibrium. Now the partial pressure we just solved for, 2.672 atmospheres. The volume of our container was given to us as 1 liter. N will now stand for the number of moles of the water. R is our gas constant, August 21st, and the Kelvin temperature was determined to be 1073 Kelvin units. Pulling out for N the number of moles, we'll hit 2.672. 2.672 divided by 0.0821 divided by 1073 Kelvin units. The number of moles of water, 0.0303 moles of water. Seeing in our equation it is indeed a 1-to-1 stoichiometric ratio, we would need the same number of moles of solid carbon. The moles of water is also equal to the number of moles of solid carbon required at equilibrium. We'll do a little mole map work. If we need 0.0303 moles of carbon, using the molar mass of 12 grams per mole, I'll go times 3 on the calculator, and we would need 0.09, and just round, 0.09 grams of carbon at equilibrium to keep this reaction going.